Weinan Lin from Peking University, and he will tell us about thick subcategories and Balmer spectrum.
Hi, everyone. Make sure that you can hear me. Okay. Hi, welcome back, and thanks, Yunze, for the introduction. So today I'll be talking about thick subcategories in Balmer spectrum. They are about something in chromatic theory called type N theory. So what's type N theory? Recall that for each n, we have Moravec's K-theory Kn with homotopy groups isomorphic to something looks like Lorentz polynomial that can have and that's invertible, and so this looks like a Bott element but in degree n, so it's n periodic. It has height exactly n, p-typical formal group law, and yesterday Zhipeng talked about this, and he also mentioned how to construct the Moravec K-theory from the MU, the complex cobordism spectrum. And here's a lemma. Let X be a finite p-local spectrum. Then the Kn homology of X is trivial, implies that the Kn-1 homology of X is 0. So then we can ask, what's the minimal n such that it's not 0? And that's the definition of the type N spectrum. So we say that a p-local finite spectrum X. Sorry, I think I may need to tell you what p-local is. I don't think someone has covered it. So basically, it's a localization on spectrum, so in algebra we have p-local rings. You do localization like a prime ideals, but on spectrum it's or in the spaces you can do similar construction. So for example, if you have the sphere spectrum, the p-localization, the effect of the p-localization in the algebra is that if you take the homology of a p-local sphere spectrum, you get the p-local integers, and that's it. And for more in-depth definition, you can Google it, or there are some references. There will be references in the end of this talk. Okay. So we say that a p-local finite spectrum X has type N if the Kn homology of X is not trivial, but the Km homology of X are all trivial for m less than n. For example, if X has type 0, remember that the K0, I don't remember if Zhipeng mentioned it. So the K0, the Moravec's K theory, when n is 0, is exactly the Eilenberg-MacLane spectrum of rational numbers. So if X has type 0, the K0 X, the K0 homology of X is exactly the rational homology of X. So X has type 0 if the rational homology is non-trivial, or equivalently if the integral homology is not a torsion group. I mean, if it has some rank, non-trivial rank. So let X be a finite p-local spectrum. Then the homology, the homology with the coefficient Fp is trivial if and only if X is trivial. So that is an effect of the p-localization. It means that we only focus on the kind of the p-torsion part in the algebra in some sense, And therefore, if you take the homology with coefficient p and you see nothing, then it means that if it's already p local, then it means that it's just trivial. And moreover, that the homology vanishes for most all values of k. I mean, if it's a finite p local spectrum, it means you can compare this to finite CW spectrum. You know that if you have a finite CW spectrum, then the homology vanishes when the degree is sufficiently large. We have a kind of a dimension theorem, and in the world of spectra, we have similar thing. Finite spectra means finite CW spectra. It's like spectra with finite many cells, and then of course the homology vanishes for almost all values of k. And then for sufficiently large n, the Atiyah-Hirschsprung spectral sequence for the Kn homology degenerates for degree reason. I mean, kind of horizontally. And if n is very large, then for degree reason, there is no non-trivial differential. And then it's easy to compute this, that when n is big, it must be the homology of x adjoined with Vn to positive -1. And it follows that if x is non-trivial, I mean a non-trivial p-local spectrum, then Knx is not trivial, because this is not trivial. Therefore, I mean the polynomial ring is not trivial. And so it means that if x is not trivial, then you can find some big n such that the Knx is not 0. And therefore, every non-trivial x has type n for some unique n. That unique n is exactly the minimal n such that this is not 0. And by convention, we say that the 0 spectrum has type infinity. Okay, so that's the definition of type n p-local finite spectrum. So if we consider finite p-local spectra of type greater than or equal to n, then we can find several formal properties of this collection. And then we make the following definition, that let T be a full subcategory of finite p-local spectra. We say that T is thick if it contains 0. And secondly, it is closed under the formation of fibers and cofibers. It means that if you have a map between two spaces that's between two objects that's in the subcategory, then the fibers or the cofibers are in this category too. And that's why it means by closed under the formation of fibers and cofibers. And lastly, every retract of a spectrum belonging to T also belongs to T. So I mean, this means that it's closed under taking a retract. Okay. So that's just a property for a full subcategory. If it satisfies these three properties, then we say that it's thick. So let T be a thick subcategory of finite p-local spectra. If X is in T, then and Y is any finite p-local spectrum, then the tensor product should also be in T. Why? So indeed, the collection of p-local finite spectra Y for which X tensor with Y is in T, it's itself thick. So I mean, all Y such that X tensor Y is in T also forms a full subcategory which is thick. Since it's not trivial, but if you think about it, it is not hard. So since it contains the p local sphere, we know that the sphere is like the unit. If you smash, here we call it tensor here. If we take the smash product of the spectrum with the sphere, then what you get is the spectrum itself. So it's like a unit. So if you tensor X with the sphere, then you get X. So of course X is in T. So the sphere is in the thick category we mentioned here, and it contains all finite p local spectra. Why? If a thick category contains the sphere, then it contains all finite p local spectra, because every finite p local spectrum admits a finite cell decomposition. So let me break this down. So we know that the thick category contains 0, and it is closed under the formation of fibers and cofibers. And remember that if you can form a cofiber of the 0 of X into the trivial spectrum, then what you get is so you can kind of form suspensions. And if you think about the CW spectra, then you can slowly build up the CW spectra by taking cofibers. So in the end, you can construct all the finite p local spectra. And this is actually copied from Lurie's notes, but I have a kind of more straightforward interpretation of the proof, that the reason that if X is in T, X tensor Y is also in T is because Y is a finite spectrum, and therefore you can slowly build up X tensor Y by taking cofibers kind of inductively, according to the gluing map of Y. So because you can decompose Y by kind of skeletons, you can add one cell by one at each time, and then you slowly build up X tensor Y. So that's exactly the same idea here. Okay. And now we have now defined the thick subcategory, and then we want to give some examples. We see that the category C greater than or equal to N, which is the collection of finite p local spectra which have type greater than or equal to N. We have defined this in the beginning about p local spectra which have type N. Here we are considering all p local spectra, all finite p local spectra which have type greater than or equal to N. Sorry, I want to. Sorry, someone has already answered the question in the chat. Okay, so here we consider all finite p local spectra with type greater than or equal to N. Then, here is an equivalent description that X is in C greater than or equal to N if and only if the Km homology of X are all trivial for M less than N. So using the long exact sequence in Km homology, we see that if we are given a cofiber sequence, X prime into X into X double prime, then if any two of them have type greater than or equal to N, then so does the third. This is easy if you consider long exact sequence. Moreover, it is clear that any retract of a spectrum of type greater than or equal to N is also of type greater than or equal to N. So I mean, just by the fact it's a retract, so that it's in homology it's an embedding. Therefore, if originally it's trivial, then the homology of the retract must be trivial too. Okay, so this means that it is thick. Remember that it obviously contains the trivial spectrum, the zero spectrum, and we just showed that C greater than or equal to N is closed under the retract and the fibers and cofibers. In the category of spectrum, cofiber sequence and fiber sequence are exactly the same thing. I mean, if this is if X double prime is the cofiber, then X prime is the fiber of this map. I mean, okay, just in case you don't know that. Okay, so we just show that this category C greater than or equal to N is thick in the category of finite p-local spectra. And then you may ask the question, are there other examples of thick subcategories? And the answer is no. These are all the thick subcategories you can see in the category of finite p-local spectra. So it's something called the thick subcategory theorem. So let T be a thick subcategory of finite p-local spectra. Then then T must be one of these. Okay, that's exactly what I just said. So today I'm not going to give the proof, but I will give it tomorrow. Okay, no question. So next, I'm going to talk about the Balmer spectrum. So if we put all the thick subcategories C greater than or equal to N together, in the definition, you can see the prime P here, but it depends on the prime. So C greater than or so for each prime P, we can define a C greater than or equal to N. And so if you put all of them together for all N greater than or equal to 1 or all P together, then we can get something called the Balmer spectrum. So more precisely, we consider we are going to do something very similar to things in commutative algebra. So here we consider a category T. It's like a symmetric monoidal category with a tensor product. I mean, it's a category where you can take tensor product of two objects, then you can get a third object. And here you have a unit object that behaves like the unit in a ring. If you take the tensor product of the one object with another object, then it's going to isomorphic to that object. And we have some coherence diagram about the properties of the tensor product, like associativity, commutativity, etc. And here we need something stronger. We need T to be a tensor triangulated category. I don't define it in the slides, but you can find the precise definition in the reference. So actually in the reference of the reference, the reference I will give will directly use this. So you have to find in the reference it gives for this. But let me explain the kind of the idea that Hannah just talked about, the triangulated category. So you can kind of think of the structure given by the triangulated category in terms of addition. So you can think of T as a as a ring, and then the triangulated category structure gives the additive structure of T. And then the tensor product here is kind of the multiplication. And the tensor triangulated category is like these two operations have to be well behaved. And you may compare this to like like in the commutative algebra, we need the multiplication in the addition to satisfy, for example, the distribution law. And here you expect something similar. Okay, there's a question in the chat. The 2 out of 3 might not hold. I think I'll leave it to the end of this talk. I'll answer the question later. Okay, and I'm just talking about that I'm comparing this category to a commutative ring, and the tensor is like the multiplication. The triangulated categories condition is like the addition, and then you can in commutative rings, in commutative algebra, we can define a spectrum. The spec it is called the Balmer spectrum of this category. So I should warn you that I mean, to avoid confusion, I should warn you that the spectrum here is different from the word spectrum in the stable homotopy category. We keep talking about spectra, but here this spectrum means something different. It's the spectrum in the algebraic geometry. It's the spectrum of prime ideals. So here the Balmer spectrum. Actually, I prefer the notation spec, but I mean when I look at the SPC, I'm more think of the space, the category of space. But yeah, anyway, so it is denoted by SPCT. It's the Balmer spectrum. That's a space whose points are the prime thick tensor ideals. So that's something different from the traditional commutative algebra. You need ideals to be thick. So here is the definition. The proper thick tensor ideals. I mean, here I'm defining what's prime here. It's actually very similar to a commutative algebra. So the thick ideals are prime if it satisfies the property that if the tensor product of two objects is in the ideal, then either one of them should be in the ideal. So you can try to think of the ideal is like a collection of objects, but since the category is essentially small, which means that it's equivalent to a small category where all objects form a set. So I mean the ideals are like sets of objects. So it's very kind of analogous to the commutative algebra. So that's the prime thick ideals. Then and we can do similar things, taking the spec of something that looks like a commutative algebra, but it's actually a category. Okay, so a basis of the open subset of the spec. So remember that the spec is a space. So we have to talk about the kind of the Zariski topology, and the topology here is given by the complements of the subset of the form. So this is also analogous to the commutative algebra. Okay, there are two. Okay, someone answered the question. Okay, in the chat. So consider the category of finite spectra denoted by this. This is the category of finite spectra. So by the 6 subcategory theorem that I stated here, these are all the 6 subcategories. So by that theorem, we can show that the Balmer spectrum of the category of finite spectra consists of these points that you consider the C greater than or equal to N for all N greater than 1 and all P, all prime P. And the topology given here, the Zariski topology. Okay, so I mean, this is kind of interesting that you can do kind of algebraic, something similar to algebraic geometry here, that you can see it put all them together and form a topological space. Okay, so what about other categories? I mean, other than the classical category of spectra and finite spectra, it'll be interesting to consider the Balmer spectrum of the category SPG of compact genuine G spectra. This is something defined in the book of Louis May Steinberg. You can find a reference in the reference I will give in the end. And actually, the title of this book is called the equivariant stable homotopy theory. So basically, I'll give you a rough idea about what this is. So some people may know G spaces. Basically, you consider a finite group G which acts on spaces, and you consider kind of the category of all those. For spectra, genuine G spectra, it's like a spectra with a G action, but actually more than that. Remember that if you have a spectra, then you can give a cohomology theory out of that. And if you have a naive G spectra, then you can think of that. Then it also give a cohomology theory. But for genuine G spectra, for ordinary cohomology theory, usually we have H0, H1, H2, which is indexed in integers. For every integer, we have a Hn. And for genuine G spectra, you can have a RG graded cohomology theory, which means that for the H1, H2, H3 correspond to the trivial representations of the group G. And the RG graded cohomology means that for every G representation, you have a cohomology HV. I mean, actually, you have a homology and cohomology H lower V, H upper V, and so it's kind of complicated. And that's what genuine G spectra gives us. It's a very rich. There are very rich structure on all those cohomology and cohomology groups. And okay, so for people who are interested in this, you can go to our website, and we have summer school in year 2019, and you can find a lot of notes. So the summer school in that year, we talk about equivariant homotopy theory, and you can find a lot of things, a lot of notes, and I guess there, I don't remember if there are video recordings, and we were talking about the equivariant spectra. You can kind of think that it's a spectra with considering the G action. Okay, so this is a very interesting category. So you may ask, what's the Balmer spectrum of that? So for each subgroup H of G, we have an exact symmetric monoidal fixed point functor. So I should warn you that in the category of G spectra, or in genuine G spectra, there are many different fixed point functors. So in classical category of spaces, we only have actually there we also have several homotopy fixed point functors, but in spectra, in G spectra, we have even more. We have a geometric fixed point functor, we have a homotopy fixed point functor, we also have categorical fixed point functor. There are several of them, and each one of them is well behaved in different sense. Okay, so here we are considering something called the geometric fixed point functor. Here it is great because it induces a continuous map of, sorry, there's a typo here, a map of Balmer spectra. So it's kind of pulled back. It maps the spec of this to the spectrum of that. Okay, and you might expect this to be something bigger, right? It's a genuine G spectrum, and therefore the spectrum might be bigger. And so studying this might not be enough to study that. But keep in mind that for every subgroup, we have such a map. So you may ask, what if we consider all these maps for all subgroups of G? And Balmer and Sanders show that all these maps are jointly surjective. So it means that you can consider all of them, and then you consider all the images. You consider the union of all the images, then they are surjective. They cover the whole thing, and that's great, right? That's kind of shows you what a set is. And but one of the problems is that you have to kind of identify different images as the you have to identify identical images. So here is what Balmer and Sanders show, that they show that P and Q are mapped to the same thing if and only if those two subgroups are conjugate, and then the two ideals have to be, you have to start from the same thing to hit the same target, and that's just one of the conditions. You also have to make sure that those two different groups are conjugate. Okay, so this identifies the image as a set because we know that all these maps are jointly surjective. But this is not enough. The spectrum is a topological space. It's not just a set. So to identify the topology on this Balmer spectrum, one needs to further identify all the inclusions between these prime ideals. So here we have a lot of things for each subgroup H, and for each N and P. I mean, basically, you can say that for each prime ideals here, you consider all of them, and you may ask which ideal is bigger. So what's the inclusions between them? And this is kind of complicated in the end. In the beginning, that the Balmers and Sanders, they have conjectures about those, but they didn't prove that. And And actually, the original statement is the original conjecture is actually not quite precise or correct enough. But later there are 6 authors. Sorry that I don't know how to pronounce all of those names. You can find those names in the reference. The 6 people they figure out the inclusion relation between them in a I think a beautiful form that so when G is an abelian group and we consider 2 subgroups of G and consider a prime P and n greater or equal to n, then the minimal I such that PKPN is included in PHPN minus I is this I. So they figure out when this ideal is contained in that ideal, and this minimal I depends on the rank of the quotient of these 2 subgroups, and the rank here is defined by the P rank here is defined by the dimension of the P torsion in A. For example, if the 2 rank of this abelian group is 3, so because it has 3 summands of G over a power of 2, and therefore the rank is 3. The 2 rank is 3. Okay, so okay. So I think I went its slides, so I went a little bit fast. So here, I give all the reference you may need in for this talk. You have Lurie's lecture notes covering the 6 subcategories, and the theory of 6 subcategories, or I should say the type N theory, is closely related to something called VN self maps or periodic self maps, and you can find a lot of those things in Ravenel's Orange book. It's about chromatic homotopy theory, and in the end, you can read this paper of 6 authors. I just mentioned. They also named the file by 6 authors, and the summer school link here. It's our summer school in 2019, and we talk about the equivariant homotopy theory. So yeah, I think that's all of my talk. I think.
Okay, so let's first thank Weinan for his great talk.
Are there any?
Right, so yeah, you have something to say?
Yeah, I think I can make some complimentary.
Okay.
So I want to say something about like the self map. I think that's kind of the motivation of all these things. For people who haven't seen those material, they might be confused about why, for example, why we care about all this type N thing. So there are something called like a periodic self map, which is if you have in a category of if you have a spectrum and you consider a self map, which means that you have a map from a suspension of the spectrum into itself, and then you can kind of take powers of that map, and if it's now homotopic in the end, it's called nilpotent. But if it's not trivial for all powers, it's called periodic. And then those periodic map it's very interesting things in chromatic theory. And then the spectrum Kn is a very good thing to detect all those periodic maps. And there's a very interesting interesting question you can ask about the type N spectrum. You can ask, are there a spectrum of type N for every N? So actually I should include this in my slides. That I haven't told you that there is an example of spectrum of type N for every N, because this is just a definition, doesn't tell you that. And the answer is yes. And it's very difficult and complicated to give a spectrum of type N for every N. And you can construct them kind of inductively. If you have a spectrum of type N, then to get a spectrum of type N plus 1, you have to construct a kind of a self map from X, from a suspension of X into X, and by the help of Kn homology, if you know enough about the Kn homology of X and what happens in the induced map between the Kn homology by the self map, and then if that map satisfies some condition from the Kn homology into the homology, then you can take the cofiber of that, then you can get something of type N plus 1. So that's the story. I mean, that's why all this matters. Yes, since I didn't expect I have extra time, but actually I should like put them for those into the slides. I think they are kind of important and interesting. Are there any questions?